okay, it's a normalizing term. So after we get all those things, okay, multiply, and we get those values. We add them up, okay, and then divide every one by that denominator. Okay, that add them up, the result, the sum is this one. Because eventually this is going to be a distribution, right? So result is going to be, if you use a computer to run this is going to be just a snap. So quick, okay? Of course, this doesn't need a computer because this is a discrete version. So easy, okay? So easy. It doesn't involve like integration at all. Okay? So we get this. So this one, if you look at this one, this is, as I said, this is posterior, right? So if you look at this posterior and the prior, you see they are slightly different, right? This is a prior, which is centered at 0.5, right? Right? But this is posterior, which is, well, it's still centered at 0.5, but obviously, these values going down a little bit, right? This value going up a little bit, right? So it becomes like this, right? Even though the center is still 0.5, but it looks like it's shifting, right? It's a little bit shifting to the right, right? Right? But this is nature. Why? Because we toast one time and the result is head. So it actually suggests that suggests that the chance of getting head seem to be a little bit higher than just fair, right? Okay, so that's why we get this one. Okay? So can you do this for more number of toasts? Obviously you could, right? Depending on how many toasts and how many head you collected. Okay? So you can do this. Okay? So okay. Basically, I already explained. But this is just an explanation of what I just told you. Okay, consider theta equal to 0.2, scanning vertically across panel. In the lower panel, 0.2, the posterior probability is likelihood from the middle panel at theta equal to 0.2 times the prior, okay, which at the theta equal to 0.2, divided by the sum of all the results. Summation of all the results. That's your evidence, or that's your that's this term, P of D. Okay, the normalizing term. Okay, so the result, is going to be, like this. Okay, so the overall contour of the posterior distribution is different from the prior distribution, as I already explained to you. Okay. So obviously you can do the similar calculation, okay, oops, sorry. You can do the similar calculation, okay, given different, number of samples, okay. So this is we have, let's look at these three figures, okay, the vertically, okay. We have this prior, okay. This prior is similar to what we had, which is centered at 0.5, okay, and linearly, decreasing on both sides, okay. And you may ask, what is this this range from 0.112 to 0.88 represent? Okay, let's not worry about that. for now, okay? We will talk about that later. Okay, that's called HCI. Okay, 95% HCI, but let's not worry about that. We'll talk about that later, okay? So, so we have that prior, and this is the likelihood that you can obtain, okay? When n is 4, z is 1. So out of 4 toes, you get 1 head. Obviously 3 tails, right? So you can, because here, obviously, originally we only consider 11 positions for theta value, right? Originally, we only consider 11, well, to be exact, we only consider 0.0, 0.1, 0.2, blah, 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 to 1.0, only 11 positions for theta value, right? But now, because we are, this one we are actually using computer to draw it, so we are able to consider much denser theta values. So I believe we consider maybe like 1,000 or 10,000 like theta values in between 0 to 1. So that's why the drawing looks like continuous. Okay, and also this one. Okay, I mean for each different theta value, you can get different value from that binomial distribution, right? Okay, I mean providing the theta value, providing the n, providing the y. Okay, so you can draw this one, and then from this one you can multiply these two to obtain this one, right? Okay, obviously you also need to normalize this. Okay, but you can see that actually this one is moving slightly toward to the left, right? Okay, this is this posterior moving, the center moving slightly toward to the left, right? And this is normal. This fits into our intuition. Why? Because out of 4 toes, we only get 1 head, right? So the chance of the head looks like it's lower than 0.5, right? Even though we have that prior, but based on the current experiment data that we collected, it looks like it's moving to, the chance of getting head is slightly lower. So you can see that we are moving toward the left, okay? And this, on the right-hand side, these 3 figure, okay? The upper figure, okay, is the prior. That prior is actually exactly the same as the left-hand side prior. Even though you look at, oh, how come the center looks like it's a little bit lower? Really, they represent the same prior, okay? It's just because the y-axis, the scale is different, okay? In this one, the y scale is larger, so that makes the height a little bit lower. But they are both exactly the same prior. They are centered at 0.5 and linearly going down on both sides, so they are exactly the same. Okay. And then in terms of data, that's interesting. Okay. Here, obviously we are talking about the same binomial distribution, obviously, right? Okay, but now, for the data that we collected here, from the experiment, we do 40 trials. We throw the coin 40 times, and we get 10 heads. Okay, So you can see that, okay, we also have 1/4 of the result to be had, right? This one we have 1/4 of the result to be had. This one we have 1/4 of the result to be had. But using the exact same binomial distribution, this is what you get. You will find that they actually both max at approximately the same place, which is 0.25. This is, well, again, this fits our intuition because, well, we get 1/4 of the result to be had. So this one, you know, the highest place is 0.25. This one, the highest place happened at 0.25. Both are like that, which is, well, which makes sense, right? But on the left-hand side, this likelihood is much more, much more slim, right? The 0.25 part is much higher than this one. Well, you may say, oh, they have the same height, but again, be very careful because we are using different scale. This one actually is narrower and wide and high and taller. Okay, than this one. Why is that? Because we have more data, right? We have more data. Okay, if you have more data, you should be more confident in the result of your data. So as a result, okay, the posterior, as you can see, okay, it moved much more closer to 0.25, right? Originally, this one, we only move a little bit towards 0.25, but this one will move much closer to 0.25, right? And it makes sense, right? Because we are using the same prior. The same prior, but the left-hand side, right, for the left-hand side and for the right-hand side, because we have more data on the right-hand side. So we should move more toward what the data suggested. As for how much we should move toward that, it depends on the Bayesian, the Bayes rule. It depends on the Bayesian data analysis. Okay? That's exactly the Bayesian analysis. Okay? So these two, okay, the difference is the amount of the data, okay, but the percentage or like the portion of the coin flipping to be had is the same, okay, and for these two, okay, we are pretty much using the exact same. We are collecting exactly the same result. Okay, left-hand side we collect like 4 toes and 1 head, and the right-hand side we have like 40 toes. Out of 40 toes, we have 10 heads. Okay, so you can see the likelihood are exactly what we have here, right? They are the same, but the difference is that, okay, we are using different prior. Okay, the left-hand side is more non-committal. Okay, meaning we do not know much about a more plausible theta value. So, well, it is not exactly uniform distribution, but it's very close to uniform distribution, right? So that means we are non-committal. We do not know which value theta is more plausible. We still center at the 0.5, but the difference is really not that much, right? That's the left-hand side the prior for the left-hand side. On the right-hand side, yeah, we are very, very sure, okay, we get this coin. The left-hand side is more like we get a coin from the magic shop. The right-hand side is more like we get a coin from the government. So we have high confidence that this coin is fair. Right? And with different prior. Okay, this one, okay, with these two, you can see the result is almost completely dominant by the data, right? This posterior is almost completely dominant by the prior because the shape looks exactly like the likelihood, right? Okay? Even though the data is weak, we don't have much data, even though the data is weak, we still are able to, the data still control it because the price is even weaker. Price is very weak, right? Okay. On the right-hand side, okay, even when you have 40 toasts, the data, we have much more data, but because the prior is strong, so you can see that, yeah, I mean, the result somewhat, is in between these two, right? With a much stronger data, I mean, we still not, you can see like the previous slide, okay? These two are almost identical, right? Because the prior is not that strong. And with more data, the data dominate the result, right? But now we have a much stronger prior, so the result is